Okay, let's start. Hi, I'm Highlight, and today I'm going to do a quick review of our 0.9.1 release. So the first part is we still have three, actually it is four. I just miss the Android prebuilt binary. So in this release, we will separate the Linux build because all of our Linux build is built with the glibc, and we have received lots of the feedback that they want to use the MUSL libc and other libc. So in next version, we were going to support multiple libc for the request. And also we have two kinds of pre-built for Mac OS, including the Intel model and the M1 model. Also, we have the Windows pre-built binary. Also, you can find the Windows installer, so you can use the installer to install WasmEdge on your Windows platform. Also, we have pre-built for the ARM64 platform for the Android. So if you want to try our WasmEdge on Android, and you can download the pre-built binary. So, and let's talk about some new features in this minor version. So the first thing is that we extended the WASI socket APIs. Most of the important part is we add the get just info, which will allow you to do the DNS query just for convert the domain name to the real IP address. So you can use the IP address to do most things. So that's the first part of our WASI socket features. And the second part, I think it's just combined with the third part, because we support the synchronized mode in our execution API. So you can create something like a promise and use the wait or cancel API to create the synchronized execution. So with this feature, now you can use our tools with limit the execution time. For example, if you set the execution time to 10 seconds, if the Watson application exceeds the 10 seconds, then it will be terminated with our interoperable API. So I believe this is the very important things in our 0.9.1 version. And also we support a new proposal called multiple memory. So in the original design, which makes you can only have one memory instance, but after this proposal enabled, you can now have multiple memory. You can have 2, 3, and more memories instance. Then we also enable the guest limitation in the CLI tools. Actually, this feature is already enabled in the CAPI. However, we forgot to expose this this feature on our CLI, so we just make it. Also, we changed and beautified the WasmEdge CLI, so you can find it become more colorful, and the information is become more clear than before. Then the last part is just the new pre-built release. I just said we support the ARM64 Android support, and which is based on the R23B SDK. Then the fix the issue and thanks for everyone, and lots of people have created an bug report, and maybe can figure out more bug in our WasmEdge, so we can fix them. And the first one is we've fixed the memory leak in the function instance, which is, somebody created lots of function instance, and they find even they terminate the WasmEdge, but there are some memory leak in those functions, so we just fix it. And the other one is that in the origin, our instruction class is very, I would say, very fat. So we just reduce the class definition. So all of our memory usage is become lower than the last version. Then thanks for the test on the Windows platform, someone figured out that some of our WASI function is not implemented correctly. For example, in this one, we actually do the fread and fwrite function. However, the return value is set wrongly. So the execution result is correct. However, because we receive the wrong return value, so we terminate the WasmEdge. Yeah, this is a very trivial bug, and we just fix them. So I think that's all of our quick review of this version. Thanks.
All right, thank you, Haidai. And are there any questions, about those new features or comments? Anyone wants to say something about that? All right, so I guess you guys should all try or check it out, right? So then we have two, I would say two features or two use cases we really want to highlight in this call. We have, perhaps 40 minutes left. That's so I want to go through some of those features and discuss that with you guys. So there's two things. The first I want to discuss is Android support. So let me share my screen. A little background, So WasmEdge is a WASM runtime that's designed to use outside of the browser, right? So it's obviously has its application in cloud computing, and where most people just use Linux, right? And we also support Windows and Mac OS and things like that as a regular server or the regular computer. However, recently there has been increasing need for us to support devices. That's in particular, we have some large organizations which I will not name right now, and you probably would see them, maybe later this year, right? Just ask us to support WasmEdge on Android devices. So the natural question to ask is why? Why do you need a WebAssembly runtime on Android? Because you already have a VM on Android. It's called the Java VM, the JVM, right? That's so the application on Android can compile to the JVM and around there. And you also have the browser, which has a WASM runtime embedded in it. Most Android devices already support WASM, through the browser. So that's so if you want to run a compiled web application, that's you can do that too. So why do someone wants to run support a WASM runtime on Android? Well, it turns out to have very good reasons. I don't know if you guys see the article that Amazon Prime Video has published. I think it's a blog post maybe a couple of weeks ago. That's we can post it in the chat. So Vivian, if you have it, you can post it in the chat. That's so it's not from AWS, but from Amazon itself. So the article talked about a challenge they faced. They have a video player. It's like Netflix, right? You can play movies and other video content on it. It's from Amazon subscribers. It's used for Amazon subscribers. So for that particular application, first of all, because it's video playback, so it has a high performance components in it, and it cannot be simply written in Java. It has to be written in some high performance language like C++ and things like that, to do video encoding and decoding. And the second, it needs to run 8,000 different kinds of devices. It's not just 8,000 devices; it's 8,000 kind of devices. And so the amount of work it takes to cross-compile those C code into different devices, and then worse, to manage those native compiled applications and update them, becomes insurmountable. It becomes very difficult. And so from that blog post, the person who wrote that blog post, who's on that technical team working Amazon, said their solution is to use WebAssembly. Is that they have a WebAssembly runtime that is embedded in the video player application, and so they compile those high performance software, the video handling code and things like that into WebAssembly, and then have this bundled in the application and then distributed to there are 8,000 devices, 8,000 types of devices, most of them being Android, right? So as you can see, the use case here is really quite interesting. Is that they are doing that in the application level. So in order for my application to run cross-platform and to have high performance, to be able to handle C++ based code, I would go to the extent of embedding a WASM runtime inside this application, right? So that's obviously this if the underlying platform being Android, that would be one of the very interesting use cases for having a WASM runtime running on Android. And perhaps even more interesting is that they had they were essentially using this the WasmEdge runtime that's embedded in the application as a middleware, essentially replacing the JVM, in those type of applications. So in order to do that, they build a UI framework on top of that. So as WebAssembly host functions, as we now all know how those works, right? That's you have a native UI framework that get plugged into a WebAssembly as host functions. So now you can write the entire application from the UI to the media processing and to device driver and all that things. They in a full stack and bundle it in a single application and get distributed to the device, right? And of course, looking at use cases like that, we know that we can take it one step further. So why limit ourselves to applications? Can't we make an entire operating system like this, right? Can't we, have alternative to Android, but without the JVM, but have WebAssembly in the middle? They're connecting the user interface to the device drivers and to everything else, right? So that's in terms of grand, the big picture of why we need WASM on Android is, the answer would be that, that's, there's lots of things that you can actually do, to make it, to make WASM the new middle tier for mobile devices or for IoT devices, right? So, so in all those cases, it's either embedded in application or it's becomes a new JVM in the operating system. That's we both need. That's a compelling WASM runtime to be compiled and to run on Android, and that's why we did it, right? That's why our partners want us to do this demo. So in summary, there's several use cases. There are several reasons why you want WasmEdge or WebAssembly in general running on Android. And the first, of course, is native speed and sandbox security for Android apps. That's essentially, at the operating system level as a JVM replacement on devices like Android, right? And the thing about JVM is only support one family of languages, the Java language, and the variations of that, like Groovy and things like that. But with WebAssembly, we can support compiled languages, especially things like Rust, C++, and things like that. But also we can support scripting languages. So as we can see on WasmEdge, we have pretty good support for JavaScript, including network applications with JavaScript, as we would see in our next topic, right? And the other benefit of having WebAssembly running on Android is that it's provide a way for Android applications to embed third-party functions. Turning your Android application into a platform. So it's have to be some kind of engine. So other people can write programs on top of your application and deploy their functions. On their device, by embedding their logic or their functions or their programs into your Android application, right? And while Android is, when people heard about Android, they always think about cell phones, but Android is used much more than cell phones. It's used in a lot of IoT devices that do not necessarily have a UI. So in those cases, you say in factories or in automobiles and things like that, you could have Kubernetes managed Android applications by having edge-friendly or edge-optimized Kubernetes distributions that can manage those Android devices from edge servers, right? So that's also part of the work that we have done. That's WasmEdge we can demonstrate WasmEdge working with, say, KubeEdge, SuperEdge, OpenYARD. So those are edge-optimized Kubernetes frameworks. So those are the some of the reasons why we want to run WebAssembly on Android. It's a JVM replacement. More language support, more embeddability, more capability to embed applications on it. So if you're interested in how to, because our official release doesn't have an Android target, but if you are interested in how to build from source code to Android, you can see this article. There's we have a comprehensive set of instructions in terms of how to build it and how to test it, and both on Android emulator and on Android devices. And if you look at, let me go back. So once you build the software, there's the requirement we have is really not only just to run WebAssembly on Android, but run WasmEdge's unique extension, which is AI inference, right? To run a TensorFlow-like model in WasmEdge, and to make it to do image recognition on Android device itself, right? So in order to do that, we have to compile our WasmEdge TensorFlow extension and also all the dependencies, names those TensorFlow libraries for this extension into an ARM format, an ARM CPU format that is accessible to the Android, right? So that's essentially, if you look at this guide, there's essentially teaches you how to do that, and how to install, once you have it compiled, how to install that, and how to install WasmEdge or compiled WasmEdge binaries onto your Android device. And from the emulator or from the real device, you can try some sample applications by using command line tools. There's ADB tools for Android devices where you can connect to your Android device and operate it from a terminal on your computer, right? So from that computer, you can use command line tools to execute command on an Android device and see see those applications run. So you can do that. You can do that in a manner that is CLI, or you can bundle that into an Android application. So Android provide a way for native programs to be embedded into Android applications. It's called NDK. So it's native development kit. As opposed to the JDK, Java development kit, right? So you don't. So on Android, you don't have to use Java. That's Java just provides a sandbox. you can also use a native language and compile it natively on the Android device. So we can take advantage of the NDK by and through the NDK route, bundle the WebAssembly runtime into the Android device and make it run other WebAssembly applications. So so this guide is also in our book. That's go through the operating systems, Android, NDK native app. It shows you how to create an Android native application using the C language, and then from that application use our C SDK, bootstrap WasmEdge runtime. So you have an Android application that starts WasmEdge runtime, and then use that WasmEdge runtime to run WebAssembly files either already on the Android device, or you're receiving from the network, right? So you can do a variety of different things by having NDK native application. It gives you the freedom to run WebAssembly files or WebAssembly modules that's on your Android devices. Right? So there's instructions how to do that and how to move those files. So once you compile those on the computer, how to move those onto an Android device and then run the example. Right? Here again, this example is a fairly complex example that does image classification, based on TensorFlow Lite model. So we can do those. That's by using the native development kit to embed WasmEdge applications into Android. And then there's the third tutorial I want to show you is to have the regular applications, the regular Android application packaged as a APK format. And so there's tools for that, and there's IDEs for that. So there's some code here that allows the APK application to call a native library, and the native library would call would be able to the native library is written in C language, and the C language uses the WasmEdge SDK to bootstrap a Wasm runtime, which runs the WebAssembly application. Right? It's long-winded, but the idea is that you have a Android APK application that's written in Java, and you want to embed WebAssembly functions in it. Those functions either something you write or your users wrote, right? That's uploaded to you, and so this approach you can do that. Basically use C language to write a wrapper that bootstrap and starts the WebAssembly run, the WasmEdge runtime, which in turn runs the WebAssembly file, and then you compile this C-based wrapper into a native library, and then use the NDK from the APK, call it, from the Java program, call this native library and achieve, what I've just said. So those are the important features of WasmEdge on Android. That's so in summary, we made it work, and it was never. We always thought it's gonna work, because Android is somewhat like Linux. It has different variations, but it's in general quite similar. And the thing that we weren't sure, but we were still able to make it work, is to have TensorFlow Lite to be fully compiled into, fully DWASD, essentially fully DWASD from its, well, to have those applications, I'm sorry, to have those applications fully compiled into APK and into the C library, and then to call the the WasmEdge, the web application from it. So that's how how we made it work with Android, and I really hope you guys would be able to try it, and maybe try it on your own device. That's or use a simulator to try it. I think that's a very interesting use case of the WasmEdge runtime, and we're gonna have more examples like this, in the future, because it seems there's a lot of need to run a non-JVM VM, a non-JVM environment sandbox on the on devices like Android and other mobile or IoT operating systems. So, for instance, we're also working on things like Open Harmony, right? And we, Raspberry Pi is really just Linux, right? It's very similar to Linux. Android is also similar, but it's different. And Open Harmony is the same kind. Is same story. And in the past, we talk about Ssr, which is a real-time operating system that is very different from Linux, right? WasmEdge as a runtime, I think it's growing its audience and to be able to run on those devices. So that's Android support. So I want to take a couple minutes pause here and see if there's questions, comments. What else do you want us to do? What would you like to see? And think that's so if you have. Then let's move on to the next topic, which is also me. And I want to tell you something that's I thought was also very interesting is to support Ssr in WasmEdge. That's a feature a lot of people have asked for. Some developers and the big companies has all asked for supporting Ssr. And in order to dive into this feature, I have to explain what is Ssr, I think, because I don't think everyone on this call are familiar with those terminologies. That's the way to build web application has changed a lot in the past, I think 5-6 years, with the emergence of new frameworks like React. Or React, always React is older than that, but Vue.js, Next.js, and things like that. It's the predominant way or the most popular way to build web application today is to write your UI not in HTML or in JavaScript, but in some high-level programming language or high-level descriptive language defined by those frameworks. It could even be in Rust. Rust, we have Vue and U. YEW and Percy and things like that. So there are lots of frameworks out there where you write your application, you write your UI, and then it has a little compiler. The compiler, what it does is compiles the application with its raw data and generates the HTML and JavaScript for you. So essentially, it's a programming language or application compiler that's the compile target is something native to the browser, right? HTML and JavaScript. And the dynamic content of this will come from the microservices on the backend. So, now we have a separation between front end and the backend. Front end is completely static website. It can be distributed over the CDN, and then the backend is microservices or serverless functions, right? So that's I would say that's the architecture of the modern web application. Well, however, then people still find a problem. The problem is the way to do that. You generate a very large, front-end package, a static website that has a lot of HTML and JavaScript in it. On the fast network, it's okay, but on the network that is slightly slow or on a device that's slow, it takes a long time for the browser to load all this and then display, and then execute all those JavaScript and display them, right? So it creates some suboptimal user experience, especially after startup. The page would become unresponsive for, I'm gonna freeze, and then it's gonna start to show its content, right? So that's, it's not the best user experience, and it's very bad for SEO. Because Google actually penalizes this behavior. Google wants your web page to be visible very very quickly, right? As soon as it loads. So Ssr was invented at the time, to do. Now we have separation between front end and back end, but instead of having the front end entirely rendered in the browser, why can't we have the front end rendered on the server, but not really on the backend server? Because if we go all the way to backend to render HTML, then it becomes the old generation, right? It becomes, the HTML and the CSS and all that is rendered from the server. So not really from the true backend, but from an intermediate place that is in the CDN or on the edge server. It's called the middle tier, right? It's an edge cloud. So where you have those edge computing nodes, where it can do those what SSR functions, essentially behaving like browsers. So the browser has a whole bunch of JavaScript and to render those DOM objects and all that. But instead of doing that in the browser, we execute those JavaScript and build those DOM objects on the server, on the edge server. And once we have those HTML and have the things to display, we send it back to the client or the browser to display it. So that's so initially, with this setup, the page come up very fast, but the page has essentially is an empty page. You just have the closing and end HTML tags and and the empty blocks that's on the page, and all the empty blocks gonna show waiting status. And then the server, the edge server spin up a process to run those JavaScript or run whatever is being sent to the server, to the client, and build the DOM and build the UI, and then stream those UI back to the client and to the browser to render. Right. This is called SSR, server-side rendering. And the interesting thing about that is, inside the browser, when you build a DOM model, you can have JavaScript do that, which is the most common way. So in that case, the SSR, the server has to run JavaScript because, as we just described, the SSR essentially is to running client-side code on the server side so that you can get the result faster and deliver to the client, right? Or today you can build the DOM object in WebAssembly. That's why you have all those Rust-based, client-side web framework, like Vue and Percy. They are Rust programs, but they are compiled into WebAssembly, designed to run inside the WebAssembly in the browser to build the UI, right? It gives you a non-JavaScript way, high-performance way to build your UI. So the thing that's the SSR edge function here, actually, in this case, the SSR edge function needs to run WebAssembly, right? So in both cases, I can have WasmEdge here on the edge node, on the edge cloud, because you can have WasmEdge that runs JavaScript, as we have demonstrated, last month and the months before. We can run JavaScript in WasmEdge. We can of course run Wasm applications in WasmEdge as well. So for all those web front-end frameworks like React, like Vue, like Next.js, like YEW, like Percy, and whether they are in JavaScript or in Rust, it doesn't matter anymore. That's we can handle all of them consistently on WasmEdge. So it's a long-winded way to explain why we need WasmEdge to do SSR, because that's one of the most I think that's one of the biggest need we see on the market. Is to do, because SSR is, when you think about it, it's a stateless function that is perfect for serverless, right? There's no database, everything just to compute and to compute and come up with a string, build a DOM model and come up with a string, right? So that's that's a very interesting, at least to us, a very, very interesting and a very it's a very interesting use case as we see a lot of demand from the market, right? So we built the SSR functions into WasmEdge, and we tested it on React and on a Rust framework called Percy, and we have achieved a success in both cases. That's so this paper or this page in the book that talks about JavaScript development. It talks we're gonna soon have another chapter in the Rust section as well to talk about the Rust Percy framework. How does that do SSR, right? But here, let's look at how we do that with JavaScript React, right? So there are two ways of doing SSR. One is to have everything rendered on the server and return to the browser at once, in one big chunk, so that that's essentially that's what I've just is a workflow I've just mentioned, right? That either too slow or too long to download to render everything on the in the browser. So basically, you shift some JavaScript or WebAssembly code to the server, so that you can run it on the server and then get the result back. that's called static rendering, meaning that's everything happens at once, and then you get the result, back to them, right? So there's a example application in our repository that shows exactly that. So this first piece of code is to build a it's React way to build a page. As you can see here, there's some HTML here, but it's not really HTML. It is it's a React markup. So for to help users to use real programming language instead of Java instead of HTML to build this web page. It's called page. The page has a section that is being populated by a lazy loading element, right? So that that's so the page tag would be replaced by the page class here when it's generated a static website. All this can be compiled into a single web page plus a single HTML plus JavaScript and be sent to the client side. But in our case, we would run it on the server, right? That's because we would only we would render the whole thing on the server instead of running the JavaScript on the client. We render this thing on the server and then send the HTML result back. And this demo shows this whole process, right? That's actually pulls together several technologies that we have developed internally at WasmEdge. Perhaps the most important is the WasI socket. So you have because in order to do that, you need to start a server from inside WebAssembly so that it can, after it, then the other thing is it needs to run JavaScript, right? So inside WasmEdge, you need to run JavaScript to build this, an internal model representation of this web page and serialize into HTML, and then send it over a network socket to the browser to show it, right? That's so this the static rendering example shows the whole process in action, right? But the static rendering I think is giving way to streaming rendering these days. The streaming rendering takes it to another step. So instead of having the entire web page rendered and then sent back to the client, I do that segment by segment. I can do that asynchronously. So that's the meaning. That's I have an open connection to the client that is streaming data at all times. So I give it back a very simple HTML page first. And with JavaScript, and then I continuously stream back new JavaScript code and HTML elements. So for each subpage or for each section of the page that I was rendered on the server, I would stream back the HTML and the JavaScript to be executed on the browser to fill out the content that's on the blank page, right? That's also provide even better user experience because you don't need to wait for the whole page to come all at once, right? You can have it, what they call is hydrated section by section, so that you can see the page gradually fill up. That's you're gonna see perhaps the most important content first, and then have all the other sections being filled out, right? So we have, and the key technology that needed for that is asynchronous I/O. Because if the WebAssembly runtime only have synchronous I/O, it would have to block the entire port, which it listens to, and while it's the streaming process is being processed and then getting sent back to the client, right? So it would be you would only be able to run one SSR function per TCP/IP port on your machine or on your VM, which is not super efficient, right? But with streaming I/O, you would be able to, while the data is being sent back, the process, it becomes asynchronous. While the data is being sent back, chunk by chunk, you would be able to do something else, while the connection is open all the time, right? So that's a benefit of the streaming rendering. And so here we also have a complete example, and this we can demonstrate that with GitHub Actions in our CI pipelines. That's so it has a web page, and as you can see here, it's fallback equals to loading, meaning that when this web page is first rendered and returned to the user, you would have a section, you have a header that's called "This is lazy home," and then underneath it, it would say loading. Okay, it would be waiting for the server to render the rest of the page. And now the page has, because the framework or the initial page is rendered. So as far as Google is concerned, the user experience is good. So you get a high SEO score, and the user is happy because it sees something and it sees loading. And then it continues to load, and this lazy page, once it would get loaded and it would render. Although this here is very simple, it's a very simple use case. You can just return to say, this is a lazy page, and now you have a lazy page. Then you have those two JSX files that describes the user interface, right? We deliberately set a two-second timer to show that it's truly asynchronous and it's truly a streaming setup, right? So you have those two pages that are rendered 2 seconds apart, and the second page is nested inside the first page. And now you can build the UI the same way you build any React application. And you can say, that's, you have those pages, and then you call the render to pipeable stream, so meaning that's now I have SSR functions that's running on the server, and it renders this outer page first, and then wait for 2 seconds to render the inner page. And they're gonna be sent back through the same HTTP port and the HTTP connection. And in a way that is asynchronous, in a way that is non-blocking and asynchronous, so that while it's waiting for those things, while it's waiting for the Snow network connection to finish, it can start to handle the next request and the next request, right? So that allows the server to, a single-threaded WasmEdge server to be able to handle multiple concurrent connections from different several different browsers at the same port, right? That essentially is how Node.js does it, right? So that's how we do streaming SSR. That's it combines that several things that we have, I wouldn't say we have pioneered, but we have developed here at WasmEdge. The first is be able to use JavaScript, be able to run JavaScript, not only run JavaScript, but to use JavaScript modules, both CommonJS modules and also ES6 modules. And to the extent where we can run full React applications in WasmEdge. And then the second is really to have reliable and high performance non-blocking I/O inside WasmEdge, so that we can start a whole server, a whole React server using WasmEdge alone, and allows this SSR functions that are associated with this React application to be able to not only run inside WasmEdge, but also return results in a way that is non-blocking, right? So this is the second example I want to showcase to you. That's this is something you can easily try with your own browser, with your own setup, and that's. But if you don't do that, you can also go to our GitHub pipeline and CI/CD pipeline to see how GitHub Actions runs it. Essentially, this is the result you're going to see in the browser. You're going to see a page that shows up first and says loading, and then seconds later, the text of loading is replaced with "this is lazy," something like that. And here it's the same. If you do a curl, it's the same result. You're gonna see HTML, complete HTML framework first, and then the element, the sections in it are gonna get hydrated with different sections that we're gonna render. So anyway, yeah, that's I think those I've talked long enough. That's it's close to midnight for me, so I'm incoherent. But but hopefully that I have explained. That's why we did why we did those two features. Why we made WasmEdge and the TensorFlow Lite extension run Android and have a complete demonstration of different ways of run Wasm applications on Android. And the second is how to run streaming SSR functions on, especially and the use case really is on the edge server. That's in WasmEdge as well. So that's yeah. We have a couple minutes left. if you guys want to ask questions or discuss anything, you're welcome to do so. And yeah.
Are you set up to leverage something like Ssr to pre-initialize the state of the WASM module to speed up the JS execution startup time?
Yeah, we'd love to do that. We have, that is on our list as well. But if you are interested in contributing, that we love to have, we love to have a contribution in this area as well, because I've heard of that, and saw that in I think the last time when we had the Cloud Native WASM Day, that's and someone did a demonstration, it was very impressive, but yeah, that's something we'd love to do. Yeah.
Have you experimented with running, well, I guess it wouldn't be WasmEdge per se, but the WASM module that you're generating here in a service worker client side?
Yeah, that's I think the work we do is because a lot of this depends on WASI. So and it's networking and all that. So it's not something that really available inside the browser. So in general, that's I think the core WASM specs is portable across browser and the server. That is also something that enables SSR, right? Because say if you have a framework like a Percy, it's read, you write your UI in Rust, and how do you render your Rust, once it's compiled into a static website? Of course, you can compile Rust to HTML and JavaScript, but it's far more efficient to just compile Rust into WebAssembly and JavaScript and HTML, because most of the Rust logic gonna be in WebAssembly, right? That allows us to do server-side rendering by take the WebAssembly part and run it on the server, right? That's so in that regard, that's core piece of logic is portable across the browser and the server. However, much of the work that we do here, for instance, that's because we are turning a WasmEdge into a full server. It's like a think about like a JVM, right? You can run application server in the JVM because JVM give you network and a socket and file system and all that capabilities. And in order the way that we run it on the server, we actually take advantage of all that. So it would be difficult to directly port it into the browser environment. However, I would say to use say a Rust-based web framework, you pretty much automatically have WebAssembly dependencies on the browser side, because all this application logic that you write in Rust is actually compiled into WebAssembly to run in the browser. I don't know if that answers your question, but that's yeah.
Well, the only reason I was asking is there's something I'm starting to experiment with, though. So most people, when you dive down into the details of how the modern frameworks work, like any of them, React, Angular, so on and so forth, Solid, all of them are, if you do server-side rendering, you're executing all that code and serializing that to HTML, but you have JavaScript that needs to execute on load to rehydrate the app when it gets loaded on the client side. In order for all of the event handlers and everything to be registered and the app to actually become interactive. And so there's this like huge boot up process that you can't break these apps up. And it's basically the current frameworks. It's perhaps maybe impossible to get like 100 out of 100 on page speed on mobile. On how these current frameworks operate. And if you can, let's say, people call it isomorphic JavaScript, like where you're running the same JavaScript on the server as you're on the client. Yes. But if you could maybe use like WebAssembly to basically do your rendering client side and server side, and then have some other mechanism to, actually, separate out your event handlers and know some other logic, and you could break up your code in a different way. It might give you a way to like do some isomorphic, effectively execution that's the same on the client and the server, but you could use like service workers to respond like it was like the server-side rendering, but using WebAssembly to actually serialize that HTML or whatever that response is, that sort of like mocking the HTTP request. I don't know. It's just something I'm experimenting with.
Right. Yeah. So I presume you have looked at a framework like Percy, right? That's
yeah. So the only one that's actually kind of trying to tackle this is actually a framework called Qwik, Qyik, and they're trying to by Misko Hevry, who created AngularJS, and he's not WASM focused, but they're trying to figure out how to basically get 100 out of 100 on a page speed mobile, on a mobile browser, like to try to solve this like boot up process where you're not executing, replaying the code, all the work you did on the server-side rendering again on the client, just to be able to load the app.
Yeah,
actually kind of interesting stuff, but I think WebAssembly might be helpful, both client side and server side for this, maybe.
yeah. We'd love to check it out. That's I think you're right on. I think that's one of the most interesting subjects is really is to run the same code on this exact same code on the server and the client. But right now, you're absolutely right. Even if you run on the server, you still have to do it on the client side again. If there's a way to get around that, and I think JavaScript is one thing, and WebAssembly is definitely now in terms of supporting on the server and on the Java and on the client, it's approaching where JavaScript is, right? Because JavaScript has excellent support on both client and server because of Node.js and and the browser runtime. But I think WebAssembly is approaching there as well because it's getting really good on the server as well. As we can see, we can do asynchronous, non-blocking I/O and all that. So we'd love to check it out, and if there's opportunity to do a demo with that, because the demo I showed here is React. It's still a JavaScript demo. It's just we are running not on the server side, not on Node.js. We are running on WasmEdge and QuickJS. That's the only difference, right? But we also have a demo on Percy. That's which is much closer to what you have just described. The WebAssembly, the same piece of WebAssembly code that runs on the server and on the client. We'd love to explore this more because, truth to be told, that's JavaScript doesn't really need us. That's although we can bring a lot of benefit to say running JavaScript in WebAssembly. A lot of people wants to do that primarily because because of the size, right? In order to run JavaScript on the server, you typically have to have a container, have Linux in it, and have Node in it, and have V8 in the node. So with WebAssembly, you only need a WebAssembly, that you can get rid of all those intermediate layers, so you can have significant performance gains. But it's still somewhat strange to run JavaScript inside WebAssembly, I have to say. But now we can do something like on both sides, it's both WebAssembly. It's in the browser, it's WebAssembly to begin with. I think that'd be actually much more interesting. Because that allows a runtime like ours to play nice with the V8 runtimes that that's already in the browsers. Yeah. So really appreciate that, and it's that project, right? So